These are the audio notes on Gibbs free energy. This first slide, you don't need to know who Gibbs is and that he went to Yale. However, in the reading guide, you should have written down this equation. This is one of the main equations that you need to know with Gibbs free energy. In the lab that we'll be performing on Monday, you are actually going to use this equation to solve for entropy, delta S. A couple of things to go over with this equation, however, is the units of it. Some of you may have noticed this on WebAssign. Gibbs free energy is given to you in kilojoules per mole. Enthalpy, if you remember that heat of reaction or a heat of a process, is given in kilojoules per mole. Temperature has to be in Kelvin. However, entropy is in joules per mole Kelvin. So in other words, if you're doing this calculation here and you're solving for delta G like you are in the WebAssign, you have to make sure that this is in kilojoules per mole and this is in kilojoules per mole Kelvin. Entropy values are typically a lot smaller, that's why they use joules per mole Kelvin instead. However, if you do not do a metric conversion, you will not get your units to match up. So remember, temperature in Kelvin, this is joules per mole Kelvin. I need to change my joules per mole Kelvin into kilojoules per mole Kelvin. That way, when I multiply these two, I'm at kilojoules per mole. I can subtract that from the kilojoules per mole here to get a delta G that is kilojoules per mole. The reason for this equation is Gibbs free energy is the ultimate determining factor in whether or not something is spontaneous. So it allows us to determine if something is spontaneous. What I'd like to do is go over to the smartboard and show you something that I know I showed one of my classes before. If a process is negative, that means it is spontaneous. Free energy means energy available to do work. And in a process, if you do all the work that you need to and there's leftover energy, you can give off that energy to the surroundings. Whenever a system gives off something to the surroundings, a negative value is given for that. If you want a process to be spontaneous 100% of the time, you want something that's exothermic, a negative delta H. It gives off heat. And you want something that is more disorder, positive delta S. So in this process here, no matter what the temperature is, as long as you have a negative minus a positive, it will always give you a negative value. On the other hand, a process that never works, a positive delta G, would be something endothermic. You have to put energy to make it go. It's not very spontaneous. And a negative delta S, there's less disorder afterwards. The only other two possibilities would be, what if I was exothermic with less disorder? Let's think about that mathematically. If I'm exothermic with less disorder, I have a negative minus a negative. To keep that negative, this is only spontaneous at low temperatures. Again, think about that mathematically. A negative minus a negative, as long as that second negative is small, it will work. The other way is endothermic with more disorder. In order to get that to be spontaneous at negative delta G, that can only occur at high temperatures. So again, knowing this equation mathematically is good. Like I mentioned to start off with, kilojoules per mole is the unit for delta G and for delta H. However, entropy is joules per mole Kelvin. So when you multiply that by Kelvin, the Kelvin parts cancel out. But you need to make sure your units are consistent throughout. And the second half of this slide here is showing, without really plugging in numbers to the equation, you can still determine whether or not a system is spontaneous or not just by looking at the sign of the delta H and the delta S. Those aren't the only equations that we need to be aware of when dealing with Gibbs free energy. The simplest one by far is the same that you've seen for enthalpy and entropy. The sum of the products minus the sum of the reactants.
And I don't think you need to write all this down, but remember to multiply by these stoichiometric coefficients. And if you haven't done the web assign yet, Appendix 3 in our textbook has all those values. Last equations to be aware of. The first one is we can solve for the Gibbs free energy by multiplying NFE. Well, N is the number of moles of electrons. F is what's called Faraday's constant. That is given to you on the equation sheet of 96,485 coulombs per mole electrons. Finally, E is the reduction potential. We are going to be using this equation in the lab. So you're going to measure the E by making your galvanic cell. Faraday's constant is a known value, and then how many electrons are in your balanced redox reaction would be your N value. This equation is given to you on the equation sheet as well. So again, you're given this equation, you're given the F value. You simply have to know voltage, number of electrons. Second equation. We can use Gibbs free energy to also solve for the equilibrium constant K of a reaction. And this equation is also on your equation sheet. Now we have to be careful with this one. This R is the 8.314. When you think energy, like Gibbs free energy, joules should be involved, not 0.0821 liters atmospheres per mole Kelvin. So we have to use the correct R value. Temperature, again, is going to be the 273 plus Celsius, because it has to be in Kelvin. Again, if you are solving for this equation and you have to solve for K, the inverse function of the natural log is probably the E to the X button on your calculator. I believe you will be solving for the equilibrium constant for that reaction as well. So again, you don't have to write down this large paragraph here, but that is what I'm mentioning, is that we could actually use Gibbs free energy to solve for equilibrium constants as well. That really wraps up the notes. I did have one more slide dealing with a demonstration of a rubber band when it's more ordered and more disordered. However, just to save us a little time, I thought it'd be best to go over the equations that we need to know moving forward. Because again, Gibbs free energy without math is just, here is the way to determine whether or not any type of chemical process is spontaneous.